The fundamental theorem of calculus sounds like a big deal, and guess what? It is. It's about to make our work easier, but then it's also going to let us do more things, which will then make our work more challenging, but we'll deal with that later. The theorem comes in two parts, and part one starts out by saying if f is continuous on a closed interval from a to b, then the function g of x defined by an integral from a to x of f of t dt, where x goes from a to b, that function is continuous on the closed interval from a to b, and g prime of x is equal to f. We're going to let that sink in a little bit. That is to say that if I take this function here and differentiate it, as g prime of x is equal to f of x. So the derivative with respect to x of g is like the derivative of this integral. Don't worry about the t right now. What this says is if I take a function f and I integrate it and then differentiate it, I get back what I started with, f. That is a description of inverse functions, or inverse, it's an inverse operator actually, or an inverse transformation. The point though is that differentiation is the inverse of integration. They undo each other. Let's take a moment and make sure we understand this g of x function. And it's kind of challenging to think about. So let's see what we can do. I have here the graph of a function f and a t-axis and a y-axis. The t-axis is because this is f of t dt. Oh, by the way, this t here has to match this t here. So the independent variable for the function f has to match the variable in the differential dt. And it's actually, in this case, it's a dummy variable. It's there just to say that everything works, okay? The variable, the independent variable for g is x, and x is showing up in the upper limit of the integral. So I have here the graph of a function f and a point marked on the x or on the t-axis, that's a. And for any value x, what g is going to give me is the area under the curve, or the integral, but since f is positive, the area under the curve from a to x. So this is a picture for some particular x value. Suppose x starts to get bigger. Then what I'm going to end up with, let me get rid of that x, is a larger interval that I'm integrating over. And then x can get even bigger, and the interval that I'm integrating over gets bigger, and then the value of the integral changes, right? So that's what g is. G is a function that sweeps out an integral that's the area, or the integral for f, starting at a and ends wherever x is, and then at some point there's a value b. Now we're going to spend some time understanding this g function later, and then we're pretty much going to abandon it. So we're going to leave that sit for now. What I'd like to do now is prove the first fundamental theorem of calculus. We're going to pick a couple of numbers, x and x plus h, that are in the open interval from a to b. Then we're able to say that g of x plus h minus g of x is equal to, since g of x is the integral with the upper limit of x, right? That's the input variable. When I'm looking at g of x plus h, I have the integral from a to x plus h of f of t dt, and then I can say minus, and then g of x is simply the integral from a to x of f of t dt. You may be wondering right away, why are we looking at g of x plus h minus g of x? Like, why did we start that way? Because we're going to make a statement about the derivative of g, and there's a limit definition that includes g of x plus h minus g of x. That's where we're going with this. Now, there's a property of limits that says that if I have, there's a property of definite integrals that says if I have an integral that goes from a to x plus h, for instance, then I can split it up into an integral from a to x added to an integral from x to x plus h. And I have a visual down here to kind of point out what I just did, right? we have an integral from a to x plus h, say that's a to x plus h, and I split it up from a to x, and then from x to x plus h. For both of them, the integrand is f of t dt. And then we still had the second term of minus the integral from a to x of f of t dt, and guess what? These two subtract out. So I've now secured that g of x plus h minus g of x is equal to the integral from x to x plus h of f of t dt. Now we said in the statement of the theorem that f is continuous on the interval from a to b. There then exist two numbers, u and v, in the interval from x to x plus h, which is inside of ab, such that f of u is equal to lowercase m, which is what I'm going to call the absolute minimum, and f of v is equal to uppercase m, which I'll call the absolute maximum. And that holds true, remember f is continuous, by the extreme value theorem. It follows that the integral from x to x plus h of f of t dt is in size between lower m times h and lowercase m times h and uppercase m times h by a comparison theorem, or a comparison property rather, of definite integrals. Now, remember that a derivative is a quotient, right? Like that g of x plus h minus g of x is going to be divided by h, and guess what? Here, we're going to divide by h. If h is positive, then we have lowercase m is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is in turn less than or equal to m, uppercase m. And h was positive, I mean, sorry, with h is positive because the inequality symbols would have to reverse otherwise. But if they did, it won't change what's about to happen. So we'll say similarly for a negative h. Now, as I just said, we know that we're dealing with a difference quotient. We're also dealing with a limit, right, as h approaches 0. And what we can say is as h approaches 0, u is going to approach x, and v is going to approach x. Reason for that, let's look up here. And suppose inside this interval, we have somewhere a u and a v. I don't care which one's bigger. It doesn't matter for what's about to happen. We just said as h approaches 0. See, you can see that u and v are going to both tend toward x. So the limit as h approaches 0 of f of u is equal to the limit as u approaches x. You see, one is happening as the other is happening, of f of u, and is equal to the limit as v approaches x of f of v. And they're both going to be f of x. Why? Because I have a limit here as u approaches x, and f is continuous. In particular, it's continuous at x. Now, lowercase m was f of u, and uppercase m was f of v. The limit as h approaches 0 of both of those is f of x. So I get to say then that f of x is less than or equal to, leave a gap, less than or equal to f of x. And in the middle, we have the limit as h approaches 0, right? So I mean, I've applied the limit. That's how we got f of x over here and over here. So now I'll apply the limit in the middle. But remember that we said way up here that the integral from x to x plus h of f of t dt is g of x plus h minus g of x. So this is the limit as h approaches 0 of g of x plus h minus g of x divided by h, which means that g prime of x, wow, is equal to f of x by the squeeze theorem. And that last result there, that's what we were trying to prove. So we are done.